Hello, this is part 2 in a video I'm calling Singular Value Decomposition, part 2. And it's a follow-up from this one, part 1, the Singular Value Decomposition. So if you haven't watched this one, I'd recommend watching that one first. But in here, we talk about the Singular Value Decomposition theorem, which basically says if we have a matrix X that's an m by n, and with rank R, it can be decomposed into this, PDQ prime, where P and G are orthogonal m by m and m by n matrices respectively, and D is an m by n diagonal matrix. And diagonal is in quotes because it's not always a square matrix, but the diagonals of the part that is squarish, have the eigenvalues down it, or the elements down it. Now, one note here is that the P and Q, it says they're orthogonal, but actually they're orthonormal. And so it's more than orthogonal. And so, and I'll point this out when I look at the singular value decomposition for a row vector. And I'm also going to do a column vector because that's kind of neat to see in itself. And then this theorem here, which is in follow-up to the singular value decomposition, this one is often quoted, but it's not quite this theorem. So where does it come from and how does it play? And that's what I want to illustrate here. So for a theorem in this video, part 2, if X is an m by n matrix with rank R, then there exists an m by R matrix and an n by R matrix. They're orthogonal matrices, S and T, and there's an R by R diagonal matrix with positive elements. This is true, they're orthogonal, such that X can be decomposed into S, delta, and T prime. So this is sort of similar to this one, but P and Q are square matrices. They're m by m and n by n, and so these are not. They have to deal with the rank of X. And so, but this one is quoted in a lot of proofs, and I wanted to show it. So here's the proof. So from background video 1, we noted that X can be decomposed into this, PDQ, where P and Q and actually D were developed like this. So P1 was an n by R, m by R. Let me see. X is m by n. Yeah, so that's m by R because it has m rows, so this has to have m rows. And it has R columns, the same as this. And then this diagonal in quotes matrix D is this, where the elements that are here, the positive elements, we call delta, and this is a square R by R matrix. And then Q can be written like this, where this is n by R. So when you do this multiplication, so let's multiply this times each of those, and you get this matrix. And of course, this just comes down. And then when you multiply this, you get this piece. So X is really just these pieces right here. But that satisfies this theorem. P1 is m by R, and Q1 is n by R, and delta is an R by R matrix. So if we let S be P1 and T be Q, then it satisfies this requirement. And so they don't quite have to be square matrices. Anyway, but this one is quoted in a lot of theorems, and so that's why I wanted to point this out. Another point, though, is these matrices, S and T, are not only orthogonal, they're orthonormal. And that'll come into play in my second example here. So let's find the SVD of a vector. And so first of all, let's assume it's a column vector, n by 1, which it's only one vector, so it has rank 1. And that means that according to the SVD, singular value decomposition, this P matrix is n by n, D is going to be n by 1, and Q is going to be 1 by 1. And you find that by this method. So it's x prime x, y equal to lambda squared y. So the eigenvector and eigenvalue for this matrix is what we're going to use. And that's how we developed Q. But notice that this is a 1 by 1 matrix. So it's a scalar. And so y is a scalar. And so clearly if you put a 1 in here, then, if this is true, then it's, then we find the eigenvector and 1 satisfies it. So y equal 1 is an eigenvector. Now if you put in 1, of course that means that this product is lambda squared, so lambda is the square root of x prime x. Remember, these are vectors, so this is a number. So Q is 1. Now there's no Q2 because this is how many it should be, 1 by 1. And delta is lambda, so it's the principal root of the eigenvalue of this matrix, which is lambda, which that says D is lambda and then all zeros, and it has to be n by 1. And P1 we develop like this. And then if you plug in X, of course, is here, and Q1, which is 1, and inverse of delta is 1 over lambda. But then to make it P, you put P1 here, and then you fill in all these columns to make this whole matrix orthonormal. Then we get this, PD Q prime. So P is this, D is this, Q is just 1. And then, of course, since it's 1, you can kind of get rid of it, and then you multiply this up, and you get lambda P1. But P1 was this, so you plug it in, lambdas cancel, and you get X. And that should be our original X, right? That's what we were decomposing. But notice that it's P1, P1 delta, which is this, Q. So it's that reduced matrix form. But let's look at a row vector, 1 by m vector with rank 1, of course. So that means P is 1 by 1, D is 1 by n, Q is m by m, according to the SVD. Now, if we're trying to find the eigenvalue and vector for this, we get this equation, we assume that it's true. So then that means Q, which is Q1, Q2, and since the rank is 1, this is a m by 1 vector, okay? And it's the eigenvectors for this, which is just y. Now, then we fill in the rest of these to make this orthonormal. And notice that the rest of these eigenvalues are associated with 0. So this is actually in the orthogonal complement space of the column space of X. That'll play a part in a second. So then delta is just the principal root of this eigenvalue, so it's just lambda. And that means D is lambda and then all the rest zeros, such that it makes it 1 by n. P1 is developed by X, Q1 inverse of delta, but Q1 was Y, that eigenvector, and this, of course, is just 1 over lambda. So we get this relationship. P1 is this. But remember, this is a 1 by m, and this is m by 1. So this is a number. This is 1 by 1 matrix. And of course, that's what P should be. So P is just P1. Then this holds, so PDQ prime is PDQ, and then multiply this into here, and you get P1 lambda 0, and then you multiply this, and you get this. So it's lambda P1 lambda prime. But P1 is this. And now notice the lambdas cancel. And so, and that's x, y. So we get x, y, y prime. Now, this is supposed to equal x, right? That's what we decomposed it into. But it's this, x, y, y prime. So how in the world is that x? It is x, and I'm going to explain it in just a second. So remember, Q is orthonormal. So if we take Q, Q prime, this is the identity matrix, right? But let's plug in what we know for Q. Q was y, and then Q2, whichever, these were the whatever vectors made it orthonormal. And then Q prime, of course, is this. So then when you do this matrix multiplication, you get y, y prime plus Q2, Q2 prime. But this is equal to I. So we can solve for y, y prime. So take that over, and you get this. Y, y prime is this. Now let's take both sides times left multiplied by x, right? So then we get this. So when we multiply this x into here, x identity is x, and so we get here. But notice that this is a row vector right here. It's 1 by m, and these columns were made to be orthonormal to the orthogonal complement space of the column space of x. So this is 0, right? Because that's by definition, this dot product, or this has to be 0. So we're left with just x. And that's why this is x. Well, anyway, that's all I have for today. Hope you enjoyed that. Hopefully it clarified some things about the singular value decomposition theorem. At least that was the goal. Like the video and subscribe so you don't miss the next one. Thanks. Bye.